Hi, how you all doing? Right, a question I'm often asked is, why is it when you integrate 1 over x, you get natural log of x plus c? And I've written it on the board here. So why is it this integral 1 over x dx is equal to the natural log of x plus c? Okay, a very good question. Now, in my first integration video I don't know if you watched it or not, but in my first integration video I did state the general rule of integration, which was this. I said that when you integrate x to the power of n dx, you get 1 over n plus 1, x to the power of n plus 1, and then plus c, okay? And I did specify afterwards that that works for any real number n except for -1, okay? And then I, almost like a throwaway really, although it wasn't intentional as a throwaway, it's merely just to satisfy people's curiosity. I did then say something along the lines of, well, let's look at what happens when n is -1, x to the power of -1 is that. Okay, and that implies that in year 12, certainly, that's not in the AS Mathematics syllabus, but you'll see it again in year 13. And then I wrote down what it actually is. I said, actually, it is natural log of x plus c. And I possibly said something along the lines of, you'll see that in year 13. And that was it. I moved on because it was a year 12 introduction to integration video. Okay. However, for those of you who want to know why that is, that's what I'm going to look at now. Okay. But I'm not going to answer that question like that. I'm not going to answer why is the integral of this equal to natural log of x plus c. I'm going to do the reverse of it. The reverse is, why is the derivative of that equal to 1 over x? Okay, and we can do that because integration and differentiation are the inverse of each other. Okay, so it should be implied that if you integrate 1 over x to get natural log of x, going backwards, when you differentiate natural log of x, you get 1 over x. In other words, I'm answering this question here. Why is it that 1 over x is the derivative d dx of the natural log of x, okay? Or another way of looking at it is treating this as an identity or an equation. Identity is probably best. You differentiate both sides, okay? When you differentiate the left-hand side, you get 1 over x, quite simply. If you integrate and then differentiate, you're back to where you started with, 1 over x, and then differentiate the right-hand side. Differentiating the constant value, of course, you get 0, so you just got the differential of that, the derivative of that, which is written as its d dx of natural log of x. So that's the result I'm going to be looking at, okay? And of course, if that's true, then this is true. And in mathematics, a lot of the time, you can prove results like this. You don't have to necessarily go from left to right, you can go from right to left a lot of the time, because it's simpler. In this case, it is simpler, okay? So I'm going to be looking at that, okay? Or I'm going to write the question, if y is equal to natural log of x, why is it the case that dy dx is equal to 1 over x? Okay, that's what I'm doing. Why is it the case that if y is natural log of x, dy dx is 1 over x? Okay, so I'm just going to look at that. Maybe I'll just keep this at the top. Okay, and I'll begin my short demonstration of it here. Okay, well, what I'm going to do is I'm just going to make it a little bit different. Okay, because in order to find out what the result is, I'm just going to manipulate the signs a little bit. So I'm going to do the opposite of natural logarithm, which is e to the power of. Like I said, you could do well with knowing a bit of year 13 work to know the result I'm about to give you. Okay, so e to the y is equal to x, and that works because e to the power of x is the inverse of natural logarithm of x. Okay. And then what I'm going to do is I'm just going to differentiate both sides. Maybe I'll just rewrite it as x equals e to the y, because it will please some of you. And I'm going to differentiate this time with respect to y. So I'm going to find out what dx dy is. So differentiating on the left, dx dy, on the right, you've got e to the power of y. That's the result you could do with knowing, actually, for this particular proof. That is, when you differentiate the exponential, e to the x, it stays the same, e to the x. So therefore, if you do it with respect to y, differentiate e to the y, you get e to the y. It's a lovely result, and it's helping me out, obviously, with this demonstration here, okay? And then, what you want to do is to find dy dx, because that is our goal, remember, to find what dy dx is. Take the reciprocal of both sides, that's 1 over e to the power of y. But I can also rewrite that as dy dx is equal to 1 over there, x. Okay? Because e to the power of y, we just said, was the same as x. And so that is it, okay? In just a few short steps, we can show that dy dx is 1 over x, okay? And that is it, okay? If it's the case that dy dx is 1 over x, then the reverse must hold true as well. That is, the integral going backwards of 1 over x must be natural log of x plus c, of course, okay? I'm hoping that you found that very, very useful, okay? Now, just a little bit. I'm going to tag on to the end. Why is this the case? Well, you need to have done a bit of work with exponentials really. This is a graph of y equals e to the x, and what I want to show you is that the derivative dy dx stays the same. Okay, it is e to the power of x. Okay, what we're saying is that if I choose any point on the graph, okay, and I draw a tangent on that graph, okay, quite pleased with that tangent if I'm honest. Okay, I'm always telling my students to use a ruler, and yeah, I'm quite pleased with that. What we're saying is that the gradient of the tangent at that particular point, okay, is exactly the same as the y coordinate at that point. So if I've just got a general coordinate point A where x is equal to A, then the y coordinate of that will be e to the power of A. What we're saying is that the gradient is also e to the power of A, okay? And that's a really important discovery in mathematics, okay? And I could choose any point along this exponential curve here. No matter what point I choose, the gradient of that point is always equal to the y coordinate of that point, okay? And that gives us the result that if y equals e to the x, then the gradient, the derivative dy dx is also e to the power of x, okay? And that helps me out here, you see? When it's x in terms of y, same thing holds, dx dy will be e to the power of y. An astonishingly useful result in mathematics, okay? But if you're not in year 13 yet, yeah, you've not quite looked at that completely, have you? But I'm hoping that's enough to demonstrate why this result holds true, okay? I'm hoping you enjoyed that, okay? If you didn't understand it, just watch it again, okay? And if you didn't see my first integration videos, the introduction in year 12, just watch those as well, okay? Thank you. Have a good day.